good morning. I feel immense pleasure to be here again for my course Engineering Thermodynamics. I am Dr. Dwivedi, Professor from Institute of Aeronautical Engineering, Hyderabad, India. I am today in my module 2, last topic. Name of the topic is Gibbs and Helmholtz functions and Maxwell relations. Before that, we have covered the second law of thermodynamics. From there, we have find out the entropy generation, statement of second law of thermodynamics. We have also solved some numericals. This statement of second law of thermodynamics states that the 100% if you give, you will not get the 100%. There is some losses. These losses were not defined in the first law of thermodynamics. In first law of thermodynamics, it is told that if you supply the heat, the work will be done. Or if you do some work, heat will be generated. But it is not 100% true. The direction of the energy flow is not defined, whether it is spontaneous or non-spontaneous, whether it is from the high temperature to low or from low to high temperature, or if you supply some heat, whether this work, how much work will be done and how much it will be, energy will be or heat will be consumed. So there one term came, it is known as efficiency. So the efficiency of any system is defined as the work output divided by heat in. And we have got that the efficiency of any standard cycle is always less than 100%. In this respect, we have discussed the Carnot cycle, and the Carnot cycle for a given temperature range is the highest efficiency which we can get. So if any engine we are thinking to modify or we are thinking to do some inventions or some research on the engine, we have to always keep in mind that the efficiency we cannot get more than the Carnot cycle of a given temperature, source and the sink. These things we have discussed, and also this generation of entropy, how much losses we have to obtain, how to calculate the entropy. This entropy is derived with the help of the second law of thermodynamics. Like the first law, from the first law of thermodynamics, we have achieved the two important properties, that is the internal energy U and the enthalpy H. But with the help of the second law of thermodynamics, we have also achieved one more property, that is called the entropy. And this entropy is always positive. In any system, entropy will be obtained. So that is the objective of this second law of thermodynamics. As of now, we have done so much in the last phase of this module 2, that is the second law of thermodynamics. We have also seen the use of the second law of thermodynamics. Also, their applications in the real field. These all things we have seen. In today's class, I am taking this Gibbs and Helmholtz functions. These are the very important mathematical relations. Then Maxwell relations. They are some mathematical relations of thermodynamics. Then we have the thermodynamic potential. This is the one more topic. Then we have Maxwell relations. Then we will also discuss some new statement of third law of thermodynamics. A very brief I have already discussed that, and this state about the absolute temperature and relation between absolute temperature and the entropy. In previous class, I have discussed about principles of entropy increase. We have also seen entropy generation, how the entropy is generated for any process. Statement of increase in entropy principle, availability and irreversibility of the process, decrease in availability when heat is transferred, that is the efficiency which we get. Otherwise, if you supply the 100% of heat, you should get 100% of work, but it is not. So how much it is available? If you take your source, like natural sources like ocean, your solar or wind energy, there are huge amount of energy is available. But how much we can abstract, how much we can absorb from there, how much we can use it, that is the available energy, or that is also called the exergy. Now I will discuss about Gibbs free energy. What is the meaning of Gibbs free energy? So here Gibbs free energy is defined that in internal energy U might be thought of as the energy required to create a system in the absence of changes in temperature or volume, and an additional amount of work PV must be done if the system is created from a very small volume in order to create room for the system. The Helmholtz free energy and environment at constant temperature T will contribute an amount Ts to the system, reducing the overall investment necessary for creating the system. This net energy contribution of a system created in environment temperature T from a negligible initial volume is the Gibbs free energy. So in this, the net energy contribution for a system created in environment temperature T from negligible initial volume is the Gibbs free energy. So here, this we can see here that what is the meaning of Gibbs free energy. So this G, Gibbs free energy is equal to internal energy minus absolute, the Ts plus PV. So what is this Ts? T is the absolute temperature, S is the final entropy. So energy you can get from the system environment by heating. This Ts you can get by the heating. This PV is the work to give the system final volume V at constant pressure P. So here this V is a final volume. So this is here, this is Gibbs. When the volume is very less, approximated to the zero, work is zero, that time this G is equal to U minus Ts. So this is called the Gibbs free energy, and this is very useful for calculating the real effect of energy. Next is the Helmholtz free energy. So the Helmholtz free energy F is defined by this, you can see here, F is equal to U minus Ts. Here we don't have the plus PV. It is not there. In our previous one, if you see, in this Gibbs free energy, we have this PV, but in this case, we don't have the, here this PV is not there. Okay, this is not applicable. So here the Helmholtz free energy is then a measure of the amount of energy you have to put in into create a system once the spontaneous energy transfer to the system from the environment is accounted for. So this energy is measure of the amount of energy you have to put into create a system once the spontaneous energy transfer to the system from the environment is accounted for. So if you see the one cup of tea here, so here you have the tea. So this is hotter than the environment. This is the cooler. So this heat will go, Q will be released. So if this Q, how much Q is released by the system, or how much it is transferred heat from the environment to the body or from the system and from the system to the surrounding, this is accounted for by the help of this Helmholtz free energy equation. So here internal energy minus Ts is your Helmholtz free energy, and if you take the Gibbs energy, in this PV is also considered. So that is the difference between the Helmholtz free energy and your Gibbs free energy equations. Now I will discuss about thermodynamic potentials. You know, the potential means it is the force which is trying to move the particle from one part to another part by the help of the thermodynamic changes. Or if there is a changes in heat, it has to, like a voltage. Voltage is to make the current to flow. Same way, this potential, thermodynamic potential, allows the system to flow from one to another, one process to another process, or from one point to another point. That is called the thermodynamic potential. So here, for quantities called thermodynamic potentials are useful in the chemical thermodynamics of reactions and non-cyclic processes. They are internal energy, the enthalpy, the Helmholtz free energy, and the Gibbs free energy. So these are the four things. These are the combinedly it is called the thermodynamic potential, and they are useful in the chemical thermodynamics where the reactions of the molecules, different types of chemical compositions, they take part in the reactions in the non-cyclic process, and they are the internal energy U, enthalpy H, the Helmholtz free energy F, and the Gibbs free energy G. These are the four combination, and by this four combination, these thermodynamic potentials are made. So here there is a diagram. This diagram shows about a plot of plus PV towards this bottom and minus TS in this direction. This is a minus TS. So we have seen that here that there are the four terms, that is the internal energy, that is a U, enthalpy, it is a H, Helmholtz function, it is a F, and Gibbs energy is a G. These four terms are clubbed in a plot. So the thermodynamic potentials are useful for the description of non-cyclic process. If it is a cyclic process, the thermodynamic gas equations and this all things will be applicable. But if it is non-cyclic process like chemical reactions and all, that time it is impossible to use those equations. In that situation, this thermodynamic potentials are very, very useful, and here it is describes. So it is a plus PV. They are used along with the first law of thermodynamics. System work and the entropy play a major role. So in this work and the entropy, Ts and the PV, this is the work. So what is the work? Work is what? It is PV, and entropy work by the entropy is a Ts, and that is also is equal to Q. So heat and the work. So these all things are have got some relations. So just now I have discussed about Helmholtz free energy. In this Helmholtz free energy, you have the internal energy U minus Ts. But if you see in this Gibbs, you have the Gibbs free energy, that is called the U plus PV minus Ts. So in this PV is extra here, and this PV is the work done. But in the Helmholtz function here, we are not considering the work of the system. So here we can see that this is the U, it is the internal energy. So U is the energy needed to create a system. For any system to have like one bucket of water, that bucket of water will have one internal energy. And here is the enthalpy H, this is also the property, and it is a U plus PV. So this enthalpy H is equal to energy needed to create a system plus the work needed to make room for it. So this is the internal energy plus how much work needed to make the room for it. When we talk about the Helmholtz function, in this Helmholtz function, we are not considering PV, only we are considering the Ts. So Helmholtz free energy, F is equal to energy needed to create a system minus the energy you can get from the environment. So this Ts is the energy which you will get from the environment or the surrounding. How much energy you are getting, that is the Ts. If you talk about the Gibbs free energy, that is U plus PV minus Ts. So this G is equal to total energy needed to create a system and make room for it minus the energy you can get from the environment. So here, this in Gibbs, it is H. This is the H. So we can also write here H plus minus Ts. So this H is equal to what? U plus PV. So how much energy which you can get from the surrounding or environment, that we have to reduce on this system. So here I have depicted the thermodynamic potential by the plus PV towards the bottom and the minus Ts towards the right. And if you see the U and H, this both are the property of a substance. So in this property U, if you minus it, you will get the Helmholtz free energy, and if you plus this work or you add this enthalpy, then you will get the Gibbs and free energy equation. In this, U plus PV minus Ts is the actual energy which is taking part in potential. Now I will discuss about Maxwell relations. So Maxwell relations are a set of equations in mathematics which are derivable from the symmetry of second derivatives and from the definition of the thermodynamic potentials. These relations are named for the 19th century physicist James Clerk Maxwell. So these names are given by the this Maxwell name of these equations are given, and they are the mathematical equations in thermodynamics which are derivable from the symmetry of the second derivative and from the definition of the thermodynamic potentials. The four most common Maxwell relations, I am mentioning here. So these are the Maxwell relations. So here plus dou T by dou V when entropy is a constant is equal to minus dou P by dou S when volume is a constant is equal to dou 2U by dou S dou V. This is the first equations for the relations. So if T and V is there, we can transfer from P to S when the volume is constant, and we can make the second derivative d to U by del S del V. Now if you see the next, when we take the T and the P relations, del T by del P when entropy is a constant is equal to plus del V by del S when pressure is constant. This we can write is equal to del 2H where H is enthalpy, here del S del P. Next, the third one, we can see that del S by del V when temperature is a constant is equal to plus del P by del T when V is a constant, volume is a constant. This is equal to minus del to F by del T del V, where F is equal to U minus Ts. This is the F here. The last one is, fourth one is minus del S by del P when T is a constant is equal to plus del V by del T when P is a constant, del to G by del T and del P, where this G is equal to U plus PV minus Ts. So that is the, here is the Gibbs function. Here del T by del P. So these are the four functions. These are very much useful for our thermodynamic equations, solving the problems. These things are very much useful. So here we can see where the potentials as function of their natural thermal and the mechanical variables are the internal energy U. U is the function of S and V, where S is a entropy, V is a volume. Enthalpy H is a function of entropy and the pressure. Helmholtz free energy is a function of temperature and the volume. And the Gibbs free energy is a function of temperature and the pressure. So in these different parameters are the function of different properties. So here we have these relations, and these relations are very useful for the different purposes. So derivation of Maxwell relation from Helmholtz free energy. So just one example I have taken, and this example will be I think very much useful for this finding out the Maxwell relations from the Helmholtz free energy. And you know that this Helmholtz free energy F is equal to U minus PV. So the differential form of the Helmholtz free energy is, it is this, we can see here that the differential form of Helmholtz free energy is dF is equal to minus S dt minus P dV. So we have seen that minus S is equal to dou F by dou T when V is a constant, the volume is a constant, and this P minus P is equal to dou F by dou V when T is a constant. From the symmetry of the second derivatives, so dou of dou V, dou F by dou T into V is equal to dou of dou T, dou F by dou V into T. So in that, and therefore that dou S by dou V when temperature is constant is equal to dou P by dou T when volume is constant. So we got the relations like this. We can just find out for others also. So just one example I have here quoted, and in this way we can find out the relations which are very useful for thermodynamic conversion from one property, the relations with one property to another. Like here, if you see the entropy and the volume, it can be transformed to pressure and the temperature. So with this type of relation, we can find out by the help of this Maxwell relations from the Helmholtz free energy equations. Now we will see that the third law of thermodynamics, we have already seen here that third law of thermodynamics. So what is that? The third law of thermodynamics states that the entropy of a perfect crystal at a temperature of 0 Kelvin, that is absolute 0, is equal to 0. Means if you are entropy means the losses, the chaos, it is randomness of any perfect crystal at a temperature of 0 Kelvin, at absolute 0 only, you will have absolute 0 entropy. Otherwise, in any condition, you will have some losses. So that is the third law of thermodynamics. Actually, it says the natural phenomena that in nature, you are not perfect. You will be always in some problem, in trouble. So if you are the designer, you should not go for that type of situation. There will be always losses, but the objective of any researcher is to make sure that these losses are reduced. So, at a temperature of a 0 Kelvin, the following phenomena can be observed in a closed system. So, what happens for a system when it is at the 0 Kelvin or at the absolute temperature? Thus, the system does not contain any heat. So, first thing is no heat. System will not have any heat in that. All the atoms and the molecules in the systems are at their lowest energy point. So all the atoms and the molecules are in very, very low energy level. Therefore, a system at absolute 0 has only one accessible microstate. It's a ground state. So if it is a system at absolute 0 has only one accessible microstate, that is its ground state. As per the third law of thermodynamics, the entropy of such a system is exactly 0. So in that condition, the entropy S will be 0. Other than this condition, every time it will be always greater than 0. Except in absolute temperature, when K is equal to 0, when K is not is equal to 0, S will be always greater than 0. So this is the very important law which defines the absolute 0 also, and also it says that at the absolute 0, you will not get any entropy. So this law was developed by the German chemist Walther Nernst between the year 1906 and 1912. So this is the credit goes to this fellow, that is the German scientist Walther Nernst. So now illustration of third law of thermodynamics. So in this we can see how these things are happening. So here we have one at 0 absolute temperature 0, that is called 0 Kelvin, your entropy will be 0 and this work W will be 1. But as you increase the temperature, you just heat it. You heat it and temperature is increasing, then there will be always temperature greater than 0. Entropy will be always greater than 0. This is losses will be there. And this is also greater than 1. This W will be always greater than 1 if there is a non-absolute 0 temperature. Absolute 0 is the lowest temperature which we can get. So, you cannot go less than 0 Kelvin. In this 0 Kelvin, you have entropy 0, W is equal to 1. As and when you increase the temperature greater than 0 Kelvin, there will be greater than 0 or the positive losses or the entropy will exist, and also there will be always W is greater than 1. So that is the depiction which is illustration of the third law of thermodynamics. So which indicates that this is a very cool and this is the hot. So as you are getting hotter and hotter, your losses will be very high and high. So that we have to take care of our personal issues also. We should not get hot. We should not get anger. We should not get as much you will get hot, your heart, your brain will get more temperature, and your losses, your efficiency of working, your body functions will be also disturbed. So this is not the entropy. In fact, it is not the only thermodynamic issue. It is everywhere. It is applicable in life. It is there in nature. It is there, and everywhere this phenomena exists. So few more statement of third law of thermodynamics. Just I am here depicting here. For a condensed system undergoing an isothermal process that is reversible in nature, the associated entropy change approaches zero as the associated temperatures approaches zero. That is the Ernst and the Simon. These are the people which they have explained that for a condensed system undergoing an isothermal process that is reversible in nature, the associated entropy change approaches zero as the associated temperature approaches zero. Okay, the next statement by the Gilbert Lewis: when the entropy of each and every element in their perfectly crystalline state is taken as a zero at absolute zero temperature, the entropy of every substance must have a positive finite value. However, the entropy at absolute zero can be equal to zero, as is the case when a perfect crystal is considered. So it is by the Gilbert Lewis. So what is the meaning of here? That when the entropy of each and every element in their perfectly crystalline state is taken as zero, that is at absolute zero only it is possible, the entropy of every substance must have a positive finite value for other than this. However, the entropy at absolute zero can be equal to zero, as in the case when perfect crystal is considered. So this is the statement by the Gilbert, and another one is from the Ernst and the Simon. In module 3, I will be discussing about these topics: introduction to syllabus of the module 3, pure substances, phase transformation, TS and HS diagram, PVT surfaces. This I will be discussing in my next lecture. Before that, I will take one numerical problem in this topic. These are the references which I have taken from P.K. Nog, Engineering Thermodynamics, Tata McGraw-Hill's, Eunice Senegal, and this NPTEL. Any questions you are welcome to ask. My email is ydwivedi@gmail.com. Okay, this is my email. You are welcome to ask. Also, I request to subscribe and like this channel, and you can give the comment so that I can reply. Thank you very much.
Like, share and subscribe. Hit the bell icon for more updates.